let us switch to the last speaker of this section, Sergei Sukharev. Hello, Sergei.
Do you see me?
Yeah. Okay. We can see you. We can hear you. Okay.
Okay.
Great.
Wonderful.
So now Sergei is from the University of Maryland. He will tell us about the small conductance mechanosensitive channels as a smart bacterial osmolyte release valve. Okay, please, Sergei, you can share your screen.
Do you see it now?
Not yet. You have to share the slides through the platform.
Okay. Share. I said share.
Share screen.
Yes.
You can see on the bottom.
I'm sharing my screen. You're in the show, sharing my screen, and application window, Chrome tab. It just doesn't want to share anything.
If you go back to your web browser, you on the page where the streams the conference, you should see on the bottom of your web page the set of tools. Among them, there is a share screen.
Yes, I click it. And
okay. Okay.
Do you see something?
No. Do you see the chat?
I do see the chat, but I have to cancel sharing the screen in order to do anything.
Okay, because the technical stuff is typing some hints for you. I'm not sure you can see them. I have
a PowerPoint. It's I'm trying to share the screen. So the PowerPoint is right in front of me. I'm clicking share screen. Screen sharing, at least to share screen. And then it pops a small window in front of me that is says share your screen and doesn't let me go anywhere else.
Okay. Let's see.
Sergei, can you hear me?
Yes, I do.
Hi, this is a technical moderator. Are you on the StreamYard window?
Yes, I am.
Okay. There's a bar on the bottom.
Correct.
Okay. Did you click on share screen?
Yes, I did. I did it many times. So I'll cancel it again and I'll click it again.
Did it ask to share a window or your entire screen?
Screen sharing is at least with 2 monitors. Strange thing. Screen sharing works best on a good monitor. Some screens don't. Okay, don't show these tips again and share screen.
Yeah, exactly.
And now it pops a small window.
Yeah.
Share your screen. Wants to share the contents of your screen. Choose what you like to share. Okay, application window. Fine.
Okay.
Share.
Yeah.
Now it should go.
Okay, yeah, perfect. We see them. Thank you, Sergei.
Excellent. Wow. Okay, so let me, do you see my screen now?
Yeah, yes, yeah, we can see it.
Gosh, it works. So, colleagues, I'm very grateful for the invitation. It's so nice to have a couple of days of vacation from this quarantine. You know, at least virtual. That's great. I really apologize for technical glitches. My computer gave me a little bit of trouble. So, what I would like to talk today is MscS channel. And before I start, I would like to acknowledge, first of all, my collaborators, because the beginning of all these projects was started with Robert Guy, with Klaus Schulten and Fred Sachs. There was a lot of great interactions and discussions with Roland Roth, Dirk Gillespie. My good colleague Joseph Najem is now collaborating with me. He's a bioengineer. I will show a little fragment of his work. So I'm also in close collaboration with Olga Butker, Juan Vanegas, and Rajita Rajeshwar. So we will, I will mention some of the work of Juan and Rajita. So my own group is Andrei Anishkin, the main player. He's a computational biophysicist, and a bunch of my students, Vladislav, Bradley, Ian, Miriam, and so forth. Some of these people are very, very diligent undergrads, and I would like just to acknowledge them before I run out of time. So bacteria. So I will, well, we're making a very good electrophysiological object out of these tiny, teeny beasts. And they're small, they're vulnerable, and they're vulnerable primarily in osmotic terms because they're small and the ratio of volume to the surface area is very small, so that the swelling is very fast. But they're very efficient, and you will see that. So if you have no cell wall whatsoever, and you have a vesicle of 1 micron in diameter, all that this vesicle can withstand is approximately 20 millimoles gradient of any solid inside versus outside. After that, it will swell and pop open.
Sergei, sorry,
yes.
sorry if I interrupt you again.
Yes.
But you need please to move on the slide because we still see the first slide.
Okay, what about now?
Still the first one? Okay. Okay, now we are on the 5th.
Okay, very good. So what if I do it this way? Do you see them changing?
Yeah, that's perfect.
Okay, fine.
Okay. Thank you.
So I will probably continue it this way, so it doesn't cause any further problems.
No,
so
that's
anyway, no cell wall, and this is a vesicle, and all it stands is only 20 milliosmoles difference inside versus outside. Then it will lyse. So interesting enough that bacteria survive enormous gradients. So intestinal bacteria, when they end up in rainwater, it's just a huge shock, huge gradient. Uropathogenic bacteria, they can withstand even more. And they do it in a very special way. Some bacteria have stronger cell walls, but cell wall doesn't actually rescue them. You will see it from my data. So what they actually do when they situate in a very, very dilute medium, and this water starts rushing into the cell swells, but instead of popping open, what it does, it opens a bunch of calibrated pores and actually jettisons everything out of the cell that is that's possible to expel. And that's what reduces the osmotic gradient very quickly. And what you may also see from this cartoon, you may see that this osmotic rescuing operation by these channels is actually a kinetic game. In other words, the exit of solutes from the inside of the cell should actually beat the water influx, so that the surge of tension inside the membrane doesn't reach the lytic limit. Here's a quick outline of my talk. This outline, it sounds more like an engineering term. So it's a preview. It's a preview major and relatively simple physical concepts that pertain to these channels as they act in a very, very specific context. So basically technical specifications, let's put it this way. So the osmotic rescuing mechanism is a kinetic game. You will see it very soon, and therefore response must be very fast because the swelling is very fast. They are small. So the MscS and MscL channels operate under a huge voltage. It's about 0.2 volts. That's the normal hyperpolarizing voltage on a coupling, energy coupling membrane. Therefore, they cannot leak, and therefore dewetting of the gates is the basically only means to make them leak-proof. The two channels act in a sequential manner. And what is important that in this case, inactivation of the last channel, of the low threshold channel, is the most salient property of the MscS, of the small mechanosensitive channel. So MscS structures are several, but there are some inconsistencies in the interpretation of those structures, and for this reason, I will spend a little bit of time explaining what the inconsistencies are, and actually propose some hypothetical model of the resting state of this channel, which are very well supported by functional experiments. That's what I will tell you. So lately, we've stumbled upon a very interesting event that implies surface electrostatics that defines the rates of inactivation and recovery. And this thing is still in works, but nevertheless, I would be glad to share my data and the first hypothesis to how this happens. So MscS acts in a specific context and functionally reconciles multiple physical factors in its structure, and that's why I called it SMART in the title. So the channels that I'll be talking about are two. One is MscL, the large conductance mechanosensitive channel. It was identified earlier. Together with the group in Kuhn's lab, we were lucky to isolate this channel biochemically. MscS was pinpointed in the genome and cloned by Natasha Levina a few years later. And both structures were solved by Doug Reese's group, and that was the major impetus to the entire field. So Natasha's paper of 1999, where they were able to knock out both of these channels from E. coli, suggested that probably these channels are equally important, and both channels, you see MscL here, plus you see YGGB at that time, that was MscS, minus here, but PYGGB re-expressed, so they sort of rescue bacteria in a similar way. And the question is whether MscS and MscL are essentially redundant valves. It doesn't look like that. That's my answer, and I will try to explain it better. So what we do to study the kinetics is other stop flow experiments that are equipped with the light scattering detector. And light scattering is the kinetics of light scattering. It reflects precisely the internal content of bacteria. So basically, small angle light scattering detects amplitude of small angle scattering is proportional to the difference of refractive indices inside versus outside the cell. And for this reason, the cells are seen in phase contrast, and by the same token, they beautifully scatter light. When the osmotic shock occurs, and we mix the bacteria with low osmotic medium, let's say, the scattering drops, and it drops because osmolytes leave the cell, and the difference of refractive indices drops. So that's what we watch. Here's the curve. That's the real trace of the upscattering, and it shows the following phases. The phase one is the swelling phase. It's because the cells initially just increase their volume so that the internal content gets diluted, but nothing happens before, and then the curve breaks, and this downfall of the curve is actually the action of mechanosensitive channels that release osmolytes, and then the scattering stabilizes at the level. It may fluctuate a little bit on a longer time scale due to some regulatory processes, but nevertheless, that's the major stretch of the curve that we are interested in. So the scattering is a square function of the mass of the internal osmolytes that are stored inside the cell. They're split here into permeable part, which exponentially leaves the cell. And therefore, the scattering signal is actually, it's a square of the exponent. That's how it is fit. So to illustrate that that's the kinetic game, here is the plot of the strength of the osmolyte release rate. That's 1/over tau, and as a function of the end osmolarity. So that's the magnitude of the shock in reverse. So we start with 1200, and then we go down, 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 and we drop, and we see that the rate, of course, increases because the osmotic gradient increases tremendously. What's important that when this rate flattens, which means that we use up the entire population of available mechanosensitive channels in this, that's when they start dying. So in other words, the system can be overwhelmed at very strong shocks by basically exhausting the capacity to eject the osmolytes quickly from the cell. All right, I will just briefly mention that this process can be modeled, and we utilized biochemical kinetics standard package COPASI, and we figured out that the swelling of the cell is relatively small. It's about 10–15%. The tension in the membrane rises sharply when the cell membrane is completely unfolded, and then the open probability of MscS channel, for instance, inside it sharply goes up. So the cytoplasmic osmolarity, contributed mostly by small osmolytes, drops tremendously, drops by about 40%. The light scattering drops by approximately 30%, and this corresponds to approximately 5 to 10% of all dry osmolytes that are actually leaving the cell during this time. So the magnitude of the shock becomes lethal, and the tension, when tension is above 14 millinewton per meter, that's when we have a chance to lyse the cell, and that's when they actually start dying. But before that, this spike of tension is relatively benign. So here is the actual trace. The green traces are taken on triple knockout, delta mescal, delta mescS, delta mescase. So these bugs are essentially helpless. They have no chance to release osmolytes quickly. And the purple traces are the wild type. You see that the swelling of the triple knockout leads to the release of osmolytes, but this is the signature of death because the release takes place through non-specific cracks. So all this time up to the red arrow is the time when there is still a chance to actually rescue. And then you see that mechanosensitive channels kick in, and right in the middle of this period of swelling, they immediately drop the internal osmolyte concentration. That's how they save it. That's the wild type behavior. So interestingly enough, that if we take empty cells and re-express back MscS, MscS wonderfully rescues cells, and it rescues in some sense even a little bit better than wild type, because first of all, they are slightly overexpressed, and the second thing is that actually MscL is a pretty crude instrument for release because it's large, it's completely sort of non-selective, and it doesn't inactivate. And the role of inactivation, that is a crucial feature of MscS, will be explained in detail. So just to reiterate, this is MscS, which is a small molecule. It's pentameric molecule, and 2 transmembrane domains only. And MscS is a much bigger beast. It forms smaller pore and smaller conductance, but nevertheless, it has a lot of very interesting features. So we patch clamp giant spheroplasts, and when we crank up suction or negative pressure in the pipette, then we see first the first wave of MscS channels. They saturate, and then if we keep increasing pressure, then we'll see how MscS starts flickering with about 3 times higher unitary current amplitude, but much faster events. So the fact that the midpoint of MscS is separated from MscS threshold by substantial tension is very important, because when we go back from the huge osmotic response where all MscSs and all MscS are engaged, then MscS closes first, and then MscS remains open. And when MscS remains open, it reduces tension far below the threshold from MscS. And that's what actually leads to the complete resealing of the membrane after it releases. I must explain that this fast release, which gets rid of 10% of internal dry weight of the bacterium, takes place within essentially 20-30 milliseconds. And the density of channels is estimated to be approximately 4,000 per cell. And they take almost 5% of the membrane area according to the simple estimates. So it's a very drastic event. The osmotic shock, it gets rid of everything, and the membrane needs to be reclosed. I will briefly talk about MscS. And MscS is a pentameric channel, and this model is 20 years old. In 2000, Bob Guy and I were thinking about it, and Bob Guy came up probably in like 3-4 weeks with a beautiful tilting model after Doug Reeves published homology model, actually, after Doug Reeves published his TB MscS from Mycobacterium tuberculosis structure. So what we show here that the gate is dry, and then there is a wetting event, and then the full opening. So very recently, essentially, so the expansion of the pore, in-plane expansion, the increase of the in-plane area, is approximately 23 square nanometers according to Bob Guy's model, and 20 square nanometers according to the slope of the dose response curve. So P open over P closed to the Boltzmann factor, delta E intrinsic energy that keeps it closed minus gamma delta area. So delta area is the slope, and it is 20 square nanometers in good experiments. So delta energy is huge. It's in around 50 KT. So very recently, basically this January, Rajita, Juan Vanegas, and us, we published this paper in Biophysical Journal, which provides first reliable simulations about how to drive this channel into the open state in a simulation, because Bob Guy's model was built just by hand, by his wonderful intuition. Okay, so in this case, the locally distributed tension is distributed according to some decaying function. And this decaying function organizes the lipids around the channel into one collective variable. And this variable, basically this function dies off within like 3 layers of lipids, so that the force is applied not to the rim of this simulation cell, but rather it is applied just to the rim of the protein, but the protein is not touched, only the lipid. And the channel reliably opens to the very similar state with different times. It can be simulated quickly, it can be simulated slowly. The outcome is the same. Rajita and Juan meticulously calculated the free energy profile of the opening transition at different tensions, and the delta area, the minimum, was calculated as approximately 17 square nanometers, which well corresponds to what we know about the conductance of the channel and what the stabilized or well simulated models tell us. I would like to mention that this is TB mescal. It opens a slightly smaller pore, so that the expansion is probably smaller too. Okay, dewetting. Dewetting is the thing that we noticed in our first simulations and documented it. This is a little bit exaggerated snapshot because the water may penetrate a little bit further down here, it is a very important part that indeed the gates formed in E. coli mescal by B23 and L19 are absolutely dehydrated. If you replace B23, that's the gatekeeping valence, with something slightly more hydrophilic like A3, then you will see that the nice and neat cooperative openings, they are now broken into subconductive states in a very, very fast flicker. So if you replace it with a charge with B23D, in this case, the channel spontaneously with no tension opens to the subconductive state. And in order to open it completely, you still need to apply quite a bit of tension. So this channel is extremely toxic for cells. But nevertheless, what it tells us that the wetting and dewetting events are actually organizing. They are synchronizing events that force all subunits work synchronously, as opposed to the case where the pore is completely pre-wetted. And this is this flicker reflects, of course, protein dynamics, whereas this neat, sharp transitions, they more likely reflect the dynamics of water. So we have two surfaces. We increase the diameter. There's an exchange between wetted and dewetted states. The water dynamics is faster than the dynamics of protein. That's what is expected, unless you have a very big pore, and then you will have to sit and wait for the cavitation event in order to close the channel. But nevertheless, that's the paradigm for the synchronizing action of water. So it is driven by one single wetting event. Here's another little deviation in my story. It's relatively recently published paper with Joseph, my good bioengineer buddy. So what we found that voltage actually quite strongly affects, or I wouldn't say strongly, it affects noticeably. It affects the energy of the transition. And for the wild type, the energy is huge. And what you see that the midpoint at different voltages changes its position. It means that the energy is different at different voltages. Energy of opening, which is opening under the action of tension. So tension is the stimulus, and the voltage is a modulating factor here. So wild type is modulated asymmetrically, as you see from the traces. And in one direction, the energy gets smaller. In another direction, it gets more or less constant. As you see that the midpoints are here. And this means that there is probably some kind of dipolar component in the protein. If you take V23T, precisely this mutant here, which opens at a slightly lower tension, and well, roughly 7-8 millinewton per meter instead of 12. And what it does, it actually shifts the activation curve to the left with voltage more gradually and more symmetrically, so that the energy looks like a parabola. So what we considered that maybe it's precisely the dielectric effect. Mark Sanson was talking about electrowetting. So water can be pulled into the pore. It will be pulled into the area of higher field, and that might bring more water into the pore. In our case, it's a little bit even more aggravated. It's because water that enters the subconductive state, it actually stabilizes and expands the subconductive state. So in other words, the water under that voltage in the electric field, it actually produces the work of expansion of channel. And then when it is expanded from the pre-wetted state, because it's E23T and it's fully wetted inside, then this water actually presses on the wall. It tends to displace the dielectric, which is protein, and then get to the relatively open state. And then when the pore fully opens, actually a lot of field is actually dropping in the axis resistances, but not in the pore. And this leads to basically to the closure of the channel back to the expanded state, and then it flickers back and forth. So we should remember that in our patch clamp experiments, we could only go up to 120 millivolts at maximum. So if we continue these parabolic curves to 200 millivolts, which is a normal voltage for bacteria, then we will get quite a bit of energy, and this will be driving the channel into the subconductive state and maybe into the open state. So in other words, the presence of threonine in the middle of the pore is completely untenable for a healthy bacterium. That's why it's valent. It's just invariably, it is a bulky hydrophobic residue there. Sometimes it's phenylalanine, sometimes it's a leucine or isoleucine. So that's the de-wetting story. So again, I'm switching gears, and we'll be talking about MscS now. So MscS was solved by Doug Rees's group, and when they published it in Science, they said, "Oh, look, the pore is there's a hole. Probably it's open." When we started simulating it, and we started simulating only the transmembrane domain, and even a little bit curtailed because our capacity and computer power was very small. So we started looking at the constriction, and we found that no, the water doesn't stay there. And when we tried to drag the ion across, it was very difficult. It was a huge force that required for that. So it is also de-wetted, and therefore wetting and de-wetting transitions must take place there. At the very same time, Henry Lester's group published the paper that conductance of mescal and MscS, the switching time between the open and closed state, is shorter than the resolution time of their very advanced patch clamp machine. It was shorter than 3 microseconds. And so this is the statistics of times and statistics of amplitudes, and it's very short. So it sort of very well corroborates with the idea that wetting and de-wetting is the single event that synchronizes the onset or interruption of conduction. So then one day we switched off PME in our simulations and found that the upper chamber, which is also very hydrophobic, not only the constriction itself, but upper chamber is also can be de-wetted. So we followed Gerhard Hammer's steps, and we decided, okay, let's vary the depth of the van der Waals well, basically Lennard-Jones by tweaking Lennard-Jones parameters. When it's 1 compared to the normal charm 27 at the time field, then we always see quite a bit of water here. So the starting position is half wetted outer chamber. If we reduce it to 2.8, we are right at the fence, and it's 50-50. And below that, we see a complete de-wetting of the outer chamber. So again, it's a question of the accuracy of the force field, and but it sort of suggests us that indeed the outer chamber is very close to the de-wetting region. So to check whether there is a consequence of actually inviting water here, we changed A98 and A102 as well L105 to hydrophilic residues, and we described. We found a huge change in the dwell time in the channel kinetics. So MscS is on the sluggish side, and 100 milliseconds, 200 milliseconds opening events, probably because the channel sits and waits the cavitation transition that would let it close. But once it is completely solvated already by serine substitution at A98, it gets more water, and some other parts they start closing and opening the channel faster than water does, and in this case, we see faster gating. So as we come closer to the constriction with this mutation, we have even shorter peak of the dwell time, and L105S is gating even faster than our recording system would allow us to detect. So in other words, yes, there is a strong effect of hydrophilic mutations in the pore, and strong effect on the kinetics, and apparently the outer chamber can be even dehydrated. So we sort of believe in that. Tim Rasmussen published a paper about it by putting here tryptophans and trying to conclude that from the fluorescence experiments. So we also found that the noble gas xenon, which is used as a anesthetic sometimes, very expensive anesthetic, it actually changes the behavior of MscS pore and MscS gating. So here are this experiment design came after discussions with Dirk Gillespie, who actually even had a little bit of spare cash at that time and sent us a small tank of xenon that we used for that. This is a regular dose response curve of MscS. Xenon decreases the amplitude and actually delays the opening, so that in the presence of xenon, it's a little harder to open channels. Some channels don't open at all. But also the dwell time changes. This is one realization, and another realization is this. So we studied the closing rate by fitting the closing time exponents, and we found that with xenon, there's approximately 15 to 20-fold increase in the intrinsic closing rate. So what we think about it is that xenon apparently comes to the pore and increases the rate of cavitation event that would interrupt the fully open column much quicker, and that's what leads to the faster closing rate. It's just introduces the defect in the liquid structure in the pore. I would continue now with another interesting phenomenon, which is inactivation. So what we have here, we have a well type subjected to linear ramps. And with a very sharp ramp, the full population opens completely. But with the slower and even slower ramps, we see that there is only a small fraction of channels actually open. So in other words, smart MscS figures out not only the amplitude of the stimulus, which is constant everywhere, but also the rate of application. It's the intrinsic property of the protein itself because G13A, that's the kink that breaks the TM3 helix, this mutant doesn't inactivate or inactivates very, very sluggishly, extremely sluggishly, so it's a very small fraction. So here's how we watch this process. So we open full population and see how big the current is. Then we step to the sub-saturating level and let the channel slowly adapt. It has this adaptive property. It adapts under non-saturating tensions. But if we intersperse here the test pulses, which are saturating, then we will see that actually the active population decays as well. And in the end, we have the difference between this point and the top. That's the population that went to deep sleep. So the channel opens under tension, but also under the same tension, but moderate tension. It goes to the desensitized state, and then it goes to the inactivated state. So the first idea, how does this happen, is this. So we have a closed channel, and we already had the first crystal structure with the splayed TM1, TM2 paddles. And we thought that probably that's the inactivated state because we clearly see inactivated state. So we thought that the closed state or resting state, ready to fire state, should be more compact, and the open state should be something else. So we implemented these structures in the form of models. On the left, you see the recently solved well-type MscS structure published by Eduardo Perosa. And this was in nanodiscs. We simulated this structure by for about 20 nanoseconds, 50 nanoseconds, and it sort of equilibrated a little bit. So the N termini got slightly disordered, but that's the stable cryo-EM structure. So here is the compact resting model that we think of, and what we see here, we see that the TM3s rose up a couple of helical turns. The kink is in a different place now, and the peripheral helices are tightly arranged around the TM3s so that the contact is restored and the tension acting on the peripheral helices will be transmitted to the gate. Okay.
Sorry, Sergei. Sorry to interrupt you. I'm really sorry. We are running out of time. I just have to ask you to come to your conclusions in a few minutes.
All right. I will come to my conclusions, and I will give you only one glimpse here. Is that the channel actually, when it spreads out, it actually resolves an electrostatic conflict inside. And this is the display of these anchoring arginines around the pore during inactivation. And what we see here is that the inactivation rate is, in fact, with wild-type MscS, is dependent on voltage, as well as the recovery rate is dependent on voltage. But this doesn't happen with the tryptophans instead of these arginines. So it looks like it's a Lippmann type electrowetting effect that takes place here, and that's what we suspect. That's the new result that I wanted to share with you. So the channel is the important part because when it closes, it goes to inactivated state, and it takes tension far away from the threshold for MscS, and that's what rescues the cells completely, because MscS flickers when it exceeds its own threshold. So basically, disarming MscS is the role of MscS. So here are my conclusions. I don't think I need to reiterate most of the parts. So the wetting is important. MscS terminates the response. The compact model structure provides some sort of missing link in this. Electrical double layer and Lippmann type effect also help the channel to actually restore, because inside we have negative potential, so that the channel utilizes the normal membrane potential in energized cell to drive fast recovery. So this is my conclusion. Thank you very much.
Thank you very much, Sergei. Thank you. We have a very small slot of time for some questions. Let me see if there are some questions in the chat.
I don't see anything, so because I'm sharing my screen. Although, oh no, I can see the chat. Yeah.
You can see. Okay. Still don't see any question. In the meanwhile, I have a curiosity that will show that I'm not an expert in this domain. But do you know if there are some kind of technological application of this MscS, MscL of any type? I don't know which type could be, but are you aware of any sensitive application to nano machines or something like that?
Well, yes, there is one application that I can attest, and because we use it. Would you allow me to share my screen again, or you prefer me to explain it verbally?
If you can show, I don't know if you can show again the screen.
Do you see it?
No. Yeah.
Okay. So here it is. So MscS is a sensor for intercalating substances. So imagine that you have a amphipathic substance, which is a good drug, for instance, and you want to know its partitioning coefficient into the membrane. One thing that you can do, you can use the monolayer and put it in the subphase and measure tension. And in the presence of this drug, because it intercalates into the monolayer, the lateral pressure will go up, and that would be the effect of intercalation, and you'll be able to measure the affinity this way. Interestingly enough, that MscS can be used for the same purpose because the drug shifts the activation curve to the right. And therefore, this guest molecule that exerts extra tension, extra pressure on the gate, its manifestation is the shift, so that you can measure those response curves, and you can measure the partition coefficient not into an artificial membrane, but you can measure it into the real bacterial membrane, because it's the inner membrane. Yeah. So that's where we are.
Okay. Thank you. Meanwhile, we have a question from Roland Roth about the Xenon. What concentration did you employ, and do you have experimental evidence that Xenon enters the gate?
Can you repeat the last part of the question?
Yeah. Do you have experimental evidence that Xenon enters the gate?
Oh, okay. No, we don't have experimental evidence. We just see the change in this behavior. Xenon is very difficult to control in the chamber because it is so hydrophobic that it just boils out immediately after you saturate your little beaker with the buffer in the high pressure bomb. So you saturate it at high pressure, and then you take it out, and it boils out immediately, and then you have no idea. You just immediately put it in the recording chamber, and that's how you measure these effects. They're not very well reproducible because you cannot really control the concentration of xenon in the water easily. So the effect is not huge, as you saw. It's not drastic, but it's easily measurable. It's recordable. So again, it was done without special gadgets where we can extrude the xenon saturated water into the chamber directly. We just didn't have that technical opportunity.
Okay. Another question following up Roland's question is by Alberto Giacomello, who says, did you change pressure in the xenon experiments?
No, we did not. We all worked under atmospheric pressure. We saturated the buffer the way we could and immediately injected it into the chamber. That was the way we did. Interestingly enough, it's just for those who may want to work with xenon, if you equilibrate at high pressure water in the presence of xenon, the water freezes at room temperature. So it just xenon forms a crystal lattice with water, but as soon as you drop the pressure from like 200 atmospheres down to 1 atmosphere, it melts and boils out.
Okay, so there are no more questions. So thank you again, Sergei. Thank you